Hello friends. Today I'm going to give a tutorial on the beginning of keeping track of motion in physics, what we call kinematics. This is basic, the very introduction. One of the things that we study in physics is motion. We describe motion, but we want to have a very technical, very accurate way of describing motion. And it turns out the best way to do that is through math. And so here's a basic introduction to how we do that and functions and graphs for non-accelerated motion in physics. So we'll start with looking at this diagram. I've created this little diagram. We can imagine a man running, and he's running, when we first start keeping track of him, he's at the 45 meter mark. So we can imagine there's a measuring tape stretched out, and he's kind of jogging. Stop and just think. What looks like he's going from 45 to 40 to 35 to 30. So he's moving about 5 meters per second. That's how we can think of this, right? And that's really what speed is, just in its most basic sense, right? You can see that. You can figure that out just from your common sense, right? And so that's the beginning of this. So 5 meters per second. Does that make sense for, a jog or a run? Yeah, that makes sense, right? Someone running the 100 meters in the Olympics, 10 seconds for 100 meters, that's like, 10 meters a second. That's really fast. But something like this is doable, so it's realistic. Person's running. And so I have these marks. It's as if we've dropped a bean bag every second. So every second that's gone by, we started when he was at the 45 meter mark, and then at every second we've dropped these bean bags. So what I'm going to do, actually, I'm going to label these time markers. It's important when we do this. My students often make this mistake when they're first starting out, and that's fine because then we correct it and we move on. But how do we label the first mark? Right? Well, we're going to label it as time 0. If we start a stopwatch at that time, the stopwatch doesn't read 1, it reads 0. So that's time 0, and then 1, 2, 3 seconds, etc. All right. Now we've got this diagram. This diagram is useful. We're actually getting information out of this diagram. This is one way of expressing the motion of this person. I'm going to put in parentheses here that the red is in seconds, just so it's clear for us. And so this is one way of expressing the motion. Here's another way of expressing the motion. Let's say we want to take the picture out. We just want to look at the numbers. Okay, well, that's going to be what we call a T-chart, and we can do that. Right, I've started it down here. At 0 seconds, he's at the 45 meter mark, right? At 1 second, he's at the 40 meter mark. At 2, he's at 35, and then so on down the line here with these timestamps. And then after 7 seconds, he's at the 10 meter mark. Right. Now again, if you count the dots, you count 8 dots, but don't forget, our first dot represents time 0 seconds. Okay, now this is another way of representing the motion. Right now we've got 2 models already. Right? One is this diagram, we call this a motion diagram, and then the other one is a T-chart. It's just tracking the motion, right? Where he is at every timestamp. Now that we have 2 quantities, realize that we've got 2 pieces of information. We have the time data and we have the location data, where he is at those times. So when we have 2 sets of data that are corresponding like this, we can put this into a graph. This is what graphing is, right? It's just 2 dimensions. It's 2 sets of data, 2 sets of numbers that we've correlated with each other, right? That's the input output. A graph is a way of expressing a function. And I made a video about functions. You can check that one out. And all a function is input output. Okay, and so we've got time on the bottom, position going up. The reason we put time horizontally mostly is because that's the thing that doesn't depend on anything else. The time is going, and what the time is independent of the motion of the person. But where the person is depends on the time, and that's the thing that can change, right? He could be here, he could be there. So that's usually why we put time on the horizontal axis. We consider it the independent variable. It's changing, but it's independent of the other thing. And so what did we, at time 0, now we're just plotting this, right? We can use the t-chart and plot these points. He was at time 0, he was at 45, and then at 40, 35, 30, 25, 20, 15, and then 10. Now I've plotted those points. Now I have a graph, right? And this graph represents the motion. It's another model for the motion. And now that I have a graph, all of the things that I can do in algebra class, I can do here. This is a line, right? This is a linear graph. And so I can draw that line. That represents the motion. Now realize what we've done. We've abstracted a ton of stuff. Actually, we've only abstracted 2 things, time and location. Is this a man or a woman? Is he running? Is it raining out or is it sunny? Is he on a track? Is he in the road? Is he on a boat and he's not actually running, right? There are so many aspects of reality that we've just taken away, and we've focused in on these 2 mathematical quantities, just the time and the location, these 2 things that we can measure. That's it. But now that we have that, now we can apply the math. So one of the things that we can get out of a graph is we can find the slope, right? And so finding slope, and I made another video recently about slope, what slope is. And I want you to watch that because it matters, right, for our conceptualization of what slope is. But basically, slope tells us how far over you go, how far down you go or over for every 1 unit of horizontal change. So 1 unit of horizontal change here gives us a difference of 5. We call it rise over run, right? And so the slope here is 5 over 1. But, now pay attention, because the vertical axis now, it's not just a number, it's a quantity. And it tells us something. It's not just 5, it's 5 meters. So these units matter. So the slope is 5 meters over 1 second. And if we simplify this and just treat the m and the s like algebraic symbols, this ends up being 5 meters per second. But there's a trick here, right? I forgot. Negative. We're going down. Every 1 we go to the right, we're going down 5. So what does that mean? But we end up with this thing, -5 meters per second. Now that is the velocity. This is what we call the velocity of the object, right? So velocity, when we write the v for velocity, we usually put a little arrow above it. And the reason we put the arrow above it is because for velocity, we're keeping track of direction. Direction matters. So when we look at this diagram, we'd say, what direction is this person running? Well, they're running towards the 0, starting positive and running towards 0. We would say this person is running in the negative direction. And then we would say, how fast is he running? Well, he's running 5 meters per second. In what direction? In the negative direction. So velocity is direction and magnitude. It's how fast and in what direction. And so this person is running -5 meters per second. That's also the slope. The slope is the velocity. So when you have a position versus time graph, like what this is, when you have a position versus time graph, the slope tells you the velocity. Okay. Well, if we have a graph and we have the slope, then can we get an equation? Can we get a function for this line? And the answer is yes, right? I mean, think about what is your typical equation look like for a line. It's y equals mx plus b. Now, what are all these things here, right? This is the vertical. This is the slope. This is the horizontal. And the b, that's the vertical intercept, or the y-intercept. Well, we have all those here, don't we? Except that instead of x and y, we have t and x. So it's a little bit different. So let's just translate this this is going to turn into now, so on the vertical axis, we don't have y, we have x, right, in meters. So I'm going to write x, that's going to take the place of the y, equals. Now instead of m for slope, we have v, because we just saw that the velocity is the slope. So x equals v, and then on the horizontal axis, instead of x, we have t. So x equals vt plus, okay, now what is b? The vertical intercept, well, that's this right here, right? That's the 45 that we had. If we go back over to this side, right, that's this right here. That's the position at time 0. And so we have a way of expressing position at time 0, and it looks like this. X naught, x0, or x origin, whatever you want to call it. You could even call it xi. Some people do that, x initial. But notice now we have all these elements in this function. We've just kind of translated them from, instead of y equals mx plus b, x equals vt plus x naught. And this is our basic equation for expressing linear motion, and there's no acceleration, by the way, constant velocity. So what do these things mean? This is the position, v is velocity, was slope, and it is still the slope. T is time, and x naught is the initial position. And now we can write the quantities in here. I'll just write it right here on the graph. So we've got x equals negative 5t plus 45. This is the equation for that line. Right? Now it's the equation for the line. It tells us about this graph, but also, and this is the crazy thing about physics, right? This is one of the beautiful things about physics, where it feels like we're just doing algebra. But in fact, this little equation, this little function, tells us something about reality. We're not just talking about numbers on the graph. Somehow these numbers are actually related to reality, like if this situation were actually set up. And what we could do is we could put a number in. I can't necessarily read very easily off the graph. I want to say, where was this person at 2.23 seconds? Well, it's a little hard to read and kind of line up, but I have this function, right? And the function is input, output. The input is the time, the output is the position, and it does it exactly. So I could put 2.23 in for the time, and it would tell me the exact location at that exact time, right? And so there's this perfect correspondence, this perfect description of the motion that's taking place by this mathematical thing. Okay, so what are the key ideas? First of all, just this, that there's some motion that took place in the real world, and I've got 3 models for it. Actually, I've got 4 models for it. The first model is the motion diagram. The second model is the t-chart. The third model is the graph. The fourth model is the equation. All those different things are all expressing the same motion. They're just different ways of expressing the same motion. When you're solving a problem, you're going to want to use these different models and line them up and make sure that they all kind of match up with each other. So, first lesson, we've got 4 different models for the same motion. Second important thing, when you have a position versus time graph, the slope is the velocity. Okay, and again, the negative just means the direction that the thing is going, and that in the function, that last number by itself, in this case the 45, is the initial position. So this is a basic introduction to motion, to linear, non-accelerated motion, and the different models that we have for it, and the basic equation for motion, which we write as x equals vt plus x naught. Sometimes it's even written as, x equals x naught plus vt, or x initial plus vt. So thanks for watching. Check out the other tutorials on what is a function and what is a slope to gain a deeper understanding of those things. And if you have any questions about math or physics tutorial you'd like to see, put it in the comments below or send me a message. Don't forget to like and subscribe. Thanks for watching.